So, as president of the Oregon Online Branch of AAUW, I'd like to welcome all of you, all 357 or however many eventually sign in, and tell you that you are going to have a wonderful experience listening to Dr. Charity Woodrum. Most of you, I hope all of you, got a chance to view her video. I viewed it over a couple of days, just yesterday and the day before, and saw things that I missed in the first viewing that I saw last April. I would like to also introduce several other important people that are here in attendance. I'm going to ask Gail Swain, president of AAUW California Online, to say a few words.
Just that, thank you all for coming. California Online has over 100 members from 8 different states. And this one thing great about online branches, there are people that belong to, Washington, Oregon, and California, which is great because we don't have to worry about getting up and getting dressed and going to a meeting in the freezing cold. We just get on our computers and have a good old time. Nobody knows if we even have pants on, so they don't need to know. So thank you for like I said, for putting this on. Thank you for coming. And please keep yourself muted during the presentation. And then any questions put in the chat, and we'll bring those up to Dr. Woodrum when she's ready. Thank you.
Thank you, Gail. Julie Skinner, our incoming AUW Montana president, just typed in the chat that her sound isn't working, but she's free to chime in anytime her sound is working again. I wanted to tell you that AAUW Oregon has members from 7 different states and even from Mexico. So like California, we have members from all over Oregon and other states, as well as from Mexico. I'm a member of AAUW California as well as AAUW Washington, so that I could participate in all these other branches and as a member and as a guest. So let's now hear from Dr. Charity Woodrum. You know quite a bit about her from her film, from her documentary, and I don't have a whole lot more to say because of that. I am just so impressed that our hometown girl, I'm from Southern Oregon, so Canyonville is Southern Oregon to me. Our hometown girl who lived in rural Oregon has, through perseverance, persistence, faith, friendship, loyalty, and a lot of brains, continued to climb to the top no matter what happened to her. And I would like Dr. Woodrum to carry on with her presentation, and we'll hear from Dr. Skinner a little bit later.
So yeah, most people have watched the film, and actually when we do live showings of the film, one of the first questions people want to ask me is if I'm doing okay now. So I just want to show you guys some updates. The documentary was filmed while I was in graduate school, so I'll let you know what's going on since then. And then I'll also talk about science as well. And this should take about 15 minutes because I want to leave, there's so many of you, I want to leave it open for Q&A. So yeah, I'll just start with last August 2024, I graduated with my PhD in astrophysics. This is pictures from my PhD defense day. On the left, you can see Marcia Rieke, who you might remember from the documentary. And she got me a cake that said reach for the stars, which was very sweet of her. In the middle here is a picture of my entire thesis committee. So these were the folks that decided whether I passed or failed. If you're wondering why I'm wearing a funny hat, it's a tradition at my graduate school that when on somebody's PhD defense day, if they pass, you make your friends a cardboard crown and a very silly cape that has all of your science and and stuff on it. So that's why I'm wearing this very silly cardboard hat. And then on the right here is a picture of myself with Sandy Cummings, who's the director of the documentary. And then Diana in white, she was the editor of the documentary. And one of the amazing things to come from this documentary is becoming friends with the whole film crew, including Sandy and Diana, as well as the filmographer. And then also, Dr. Fisher came to my hooding ceremony. You guys will probably remember him. He was my undergraduate research advisor at the University of Oregon. In the middle here, you can see him showing me how to put this goofy hood on that you wear to your hooding ceremony for your PhD. And there's on the left is Marcia actually putting it on me for the ceremony itself. So it was amazing that he came out and supported me for my PhD graduation. Also, a couple of months after graduating, well, first of all, during the last year of my PhD, I started taking flight lessons, and I was ready to take my exam a couple of months after my PhD defense. And so I just wanted to update you guys with that as well. The far left picture is a picture of me right after my first solo. Craziest thing I've ever done, and probably that's the most amazing I've ever felt. I don't know if this is common. This is a common thing in academia. There's something called imposter syndrome, where you think you achieve things because you fooled everybody into thinking that you're more qualified than you actually are. And this is something I certainly suffer from. But you can't be an imposter and fly an airplane by yourself. So that was a very powerful moment for me, I think. Also, it's a hobby that you can see progress happen really fast, while research, sometimes progress doesn't happen very fast. The middle picture is just a selfie that I took for my first cross-country solo, which that sounds crazy, like I'm going across the whole country. It was actually like a 3-hour flight all by myself. And then the rightmost picture is with my examiner. He's, qualified from the FAA to give me an exam. At first, it's like an oral exam, and then you actually have to fly the plane, and he does a bunch of things and make sure that, you can handle it, such as turning off the engine and making you land the plane. But yeah, so I got my pilot's license back in October. And now I'm at NASA Goddard Space Flight Center. My position is I'm a NASA Postdoctoral Fellow, and I work with the James Webb Space Telescope. And here is Sandy again, the director of the documentary. She came and visited me at NASA. And then on the bottom right, one of the things that I've been doing at NASA other than research is my boss at NASA, she's really passionate about public outreach. And she's kind of a big deal. So she goes on things like 60 Minutes and in big documentaries and stuff like that. So whenever she has an event that she doesn't really have time for, she asks me if I want to do it instead. And so last Halloween, I did what's called live shots, where you sit in the NASA studio for 2 hours and you just talk to a different news station every 10 minutes, and it's live. So that was fun. Well, I would call it type 2 fun. I don't know if you guys have heard of type 2 fun before. It's something that I heard from the rock climbing community. It's where at the time you're not exactly having fun, either because it's scary or stressful, but when you look back on it later, it seems fun. And so when I see this picture, I'm like, oh yeah, that's fun. I would do that again. And then also the last update I wanted to give is another amazing thing to come from the documentary was one of our donors, our first donors, after watching the film for the first time, she said, okay, what's the call to action? She felt like there should be something folks could do after watching the documentary if they wanted to. And so Sandy, her and I came up with the idea for Woody Stars. It's an enrichment fund. So our students get $2,500 per year, every year of their undergraduate degree. So $10,000 total. And they also get mentorship from Dr. Fisher and I. We actually all 7 of us had a meeting last Friday. And so we have group meetings, and then also they can have one-on-one meetings with me. And I just edited Paul's resume because he's applying to internships right now. And so these are the 5 stars that we have. And our qualifications for them, they're all very well qualified. And so we expect them all to be successful. But the other thing that we're looking for is students that actually need both the money as well as the mentorship. And so these are our 5 amazing students, and I could talk about them all day. Very proud of them. But yeah, as I mentioned, now I'm at NASA working as a NASA Postdoctoral Fellow, and my job is technically 100% pure research. So I just wanted to talk to you guys a little bit about my research at NASA, and I wanted to start with this image. It's called the Hubble Deep Field, and seeing this image for the first time is one of the reasons I became an astronomer in the first place, and then also it's one of the reasons that I chose my particular field, which is the field of galaxy evolution. And so I also want to give some background information about this image. So basically 30 years ago, back in the 90s, astronomers said, what if we find the darkest part in the sky and point the Hubble Space Telescope at it for 10 days? And a lot of scientists were against this idea because, you know, they thought, what if there's nothing there? And Hubble Space Telescope time, especially when it first launched, was, you know, it's extremely precious. But the director at the time wanted to see it happen. And so they did that. They used the Hubble Space Telescope, pointed it at this tiny part of the night sky, the darkest part of the night sky, for 10 whole days. And again, people weren't sure if anything would be there, but what ended up happening was this image, which is over 10,000 galaxies. And just to give you an idea, if you were to hold your thumb to the side and hold it up to the night sky, the width of your thumbnail, that's how tiny of an area this is covering. And it's what, prior to this image, we thought nothing was there. And it turns out that there's 10,000 galaxies there. And these types of deep fields are very important for my research in the field of galaxy evolution. We basically take these deep fields. So imagine, you know, this is just one image, and imagine taking a bunch of them and kind of doing like patchwork on the sky. That's how we take what are called these surveys. And with Hubble, we were able to learn a lot of things about galaxies in this way, including this is called the galaxy bimodality. So these are the two main types of galaxies. There's more types of galaxies than that, but these are the two main ones. On the left is what's called a spiral galaxy, and on the right is what's called an elliptical galaxy. And spiral galaxies have a lot of gas and dust. That's what's in their spiral arms. And that gas and dust is fuel for star formation. So they're forming a lot of stars. And then the galaxy on the right, it looks like it could be dusty. There's actually barely any gas and dust in that elliptical galaxy. It's basically full of red stars, and it no longer forms new stars. And we know with Hubble and with all of the technology of the day, we knew that, you know, starting from about 10 billion years in the past, galaxies were forming a lot of stars. So we had a lot of galaxies that looked like these spiral galaxies. And then as time went on, we started to see these elliptical galaxies or these quenched galaxies that are no longer forming stars. And so my PhD thesis was a lot about trying to understand why galaxies go from spiral galaxies to elliptical galaxies. We call this process quenching, and there's many physical mechanisms that could be responsible for it. But again, looking back at the Hubble Deep Field, with Hubble, if you pointed it at this same place in the sky for years, you still could not see the first galaxies in the universe. And that's because it was limited by its technology. And 30 years ago, the goal in astronomy was, how do we see the first galaxies in the universe? And that's how the idea for the James Webb Space Telescope came to be. The purpose of the James Webb Space Telescope was to answer questions like, how did those first galaxies form? And how do galaxies evolve over cosmic time? And the reason that JWST would be able to see those very distant galaxies is because it sees a different type of light than what Hubble sees. It sees what's called infrared light, because the universe is expanding. So when the light leaves those distant galaxies, it's optical light that you could see with your eyes. But by the time it reaches us, it's been stretched, and that makes it look very, very red, so red that it's in the infrared. And so we had to build an infrared telescope. So they came up with the idea 30 years ago. It launched a couple years ago, and it's been doing an amazing job of finding those first galaxies. In fact, folks from my team at the University of Arizona, they were the ones that held the record for the most distant galaxy. But since then, that record has been broken, and it will continue to be broken. And in the news, you may have heard this phrase used a lot. JWST is a cosmic time machine. In fact, all telescopes are a cosmic time machine. And I just kind of want to explain that concept to you all. So when you see the moon, it takes light 1.3 seconds to reach us. So you're always seeing the moon as it was 1.3 seconds in the past. The same applies to further distances. So the sun, you're always seeing the sun as it was 8 minutes in the past. And this applies to even further distances. So for example, this is our nearest massive galaxy neighbor called the Andromeda Galaxy, and it's 2.5 million light years away. So that means it takes the light 2.5 million years to reach us from Andromeda. So we're always seeing Andromeda as it was 2.5 million years in the past. And so when you look at the most distant galaxy, say, this image shows you 11 billion years ago, 4 billion years ago, all the way up until today, this is how we show how galaxies evolve over time. We look at the most distant galaxies and all the ones in between, and we basically look at the whole populations of galaxies in these different, snapshots in time, and we lay them out like a storybook. This is a close-up just to show you the power of JWST. This is a close-up within the Hubble Ultra Deep Field, and this was taken by Hubble. And this is the JWST version. So I know a lot of people, your eyes are naturally attracted to those big galaxies that have spirals and everything, but someone like me is actually looking in the background for those tiny little red smudges. Some of these are the most distant galaxies in the universe. So, JWST has seen galaxies that existed, over 13 billion years in the past. And you can see, one of the things you can see in these images is that they're all different shapes and colors and sizes. And those different properties can tell us a bit about their evolution. For example, if it's red, it could be because it's an elliptical galaxy and it's full of old stars, or it could be dusty, is another reason it could be red. So we like to take images of galaxies to get their shapes and sizes and colors. And then we also take what's called spectra, so we can actually see the chemical content of the galaxies. And since JWST has launched, one of the most significant findings, or the biggest surprise really, was that JWST has found that the early universe is more evolved than we previously thought. And you might be wondering, what do you mean by more evolved? So for example, in the early universe, the very first galaxies, they tend to be really clumpy looking, and we thought it would take a long time for a galaxy such as this spiral to form. But with JWST, we're seeing these grand spiral design galaxies much earlier in the universe than we expected. And then on the right, this is a picture of an elliptical galaxy. These just happen to be next to each other in the sky. This is an elliptical galaxy, and we're also finding these elliptical or quenched galaxies much earlier in time than we would expect to see them. So both of those things point to a universe that has evolved more quickly than we thought possible. And early on, when JWST first launched, you might have seen all of these news articles that said things like, JWST is a universe breaker. Our understanding of the universe is completely broken and everything like that. And that was because we found surprisingly massive galaxies in the early universe. So they were much more massive than we thought they should be. And actually, one of my most recent papers was addressing these findings. And in my paper, I discussed how when we are estimating the masses of these galaxies, we're using basically a ruler that's based on the nearby universe. So we're looking at the nearby universe and saying, okay, that's how galaxies work here. So, and we're making models and applying that to the galaxies that existed over 13 billion years ago. But the problem with that is the early universe was a much different place than the nearby universe. It was much denser and hotter back then. And it turns out when things are denser and hotter, star formation is different. And so you have to take that into account. And once you take that into the account, I show in my paper that no, the universe isn't broken. We just need to make better models. And then my most recent paper, I looked at the stardust in galaxies. These are all images of galaxies from JWST. These are all very nearby galaxies, very pretty. And anything glowing in red, that's stardust that you're seeing. And galaxies are collections of gas, dust, stars, and dark matter. So dust is one of the fundamental components of a galaxy. But stardust can only exist. So in the early universe, there was only basically hydrogen and helium. And this dust is made out of carbons and silicates and stuff like that. And so for that dust to exist, there has to be multiple generations of stars, and the stars have to live and die and explode, their inner core outwards so that new stars can form, and more carbons and silicates can be produced in these supernova explosions, for example. And so, for the first time, we were able to look at the dust content of distant galaxies. And also, when I say dust, so imagine zooming in on a tiny little nodule inside one of the spiral arms. If you were to zoom all the way in, this is what it would look like. There are these big clouds of gas and dust, and this is where baby stars are being formed. And so with JWST, I was able to basically add up all of the dust in these star forming regions in the most distant galaxies. And I expected to find that there would be less dust content than there would be in the nearby universe, simply because, galaxies in the nearby universe have had over 13.7 billion years to have multiple episodes of star formation. So you would expect them to have more dust, since dust is a byproduct of star formation. But what I found was that actually these early galaxies have the same amount of dust as the nearby galaxies. So that's yet again, JWST is showing us that these early galaxies are more evolved than we expected. So they're bigger, they have more dust, they have more structure in every way, basically. We're finding that they're more evolved than what we would expect. And that's the end of my presentation here. I wanted to now, now that I've given you a pretty good lecture on galaxy evolution, I just wanted to open it up to a Q&A. You guys can ask me questions about the film, about my personal life, about galaxies, JWST, whatever you want.
Thank you. I have a couple questions from the chat. The Pat Lehman asked the different rates of development. What are the implications? Pat, go ahead and unmute. Did I get your question right?
Well, I was reading recently that there are two different measurements from the Hubble and the JWST that measure the rate of expansion of the universe. And I am wondering what accounts for that discrepancy, as far as you know, and what does it mean? I'm just very curious about that.
Yeah. So as I mentioned earlier, I'm just clarifying the question for the audience. So the universe is expanding, and we have different ways to measure the expansion rate. However, the ones that use basically a picture of the very early universe, and ones that use information from the very nearby universe, they disagree with each other. And yeah, we don't know why. That's a huge open question in astrophysics right now, and there's a lot of people trying to answer that, and we don't know what the cause of that could be. A lot of people are investigating that, though. That's a good question.
Asha, I didn't get her last name, wanted to know if that one picture that looked like a hand, was that the Eagle Nebula?
That's the one I showed, was called the Pillars of Creation, which is, I forget which nebula that's in. I should know that, but it's called the Pillars of Creation. And that one in particular was taken with JWST, and it has imaging. So JWST has two main cameras. There's NIRCam, which sees near infrared light, and then there's MIRI, which sees mid infrared light. So if you want to find that picture, if you type in, Pillars of Creation, NIRCam, MIRI, it'll pull that one up. But there's also some with, yeah.
Asha Flores said, oops. Rose, would you like to unmute yourself and ask your question?
Hi there. Hi, I'm a UO PhD student right now, and I was wondering if you could tell me a little bit more about what it's like being a postdoc at NASA. Like, what does your day look like, and how do you balance research with outreach efforts?
Yeah, great question. So NASA's, you're very well aware of what academia is like, and NASA is similar in ways to academia, but one of the things that drew me to it is they have more of a work-life balance there. If you want to work, 50, 60 hours a week, of course you can, but it's not expected of you so much as it can be with academia. People just have more work-life balance. And then it's naturally collaborative. So in academia, you can totally find collaborative environments. And I've actually been very lucky for that to be the case in my academic career. However, at NASA, it's kind of built into everything about NASA is about, working together. We're all working together for humanity, and it's everything that we do is for the public as well. As far as doing research as well as outreach, that's something that is a struggle, I would say, but I'm very passionate about the outreach, and sometimes it helps me stay motivated to keep doing my research. So I think it helps my research in that way.
Great. Okay, Cassidy, go ahead.
Hi, I'm Cassidy. I've wanted to be an astronaut since I was 2 years old, and I've also won a PhD in astrophysics just like you. And I was wondering, what do you think my undergraduate degree should be, or like what would be a good place to go if I wanted to study something like that?
Yeah. So if you want to be an I actually applied to be an astronaut, and I was rejected. I knew I was going to get rejected, but I was still proud that I was qualified and I applied. I think if I were to do it all over again with the goal of being an astronaut in particular, and if you want to, so yeah, there's two routes you can go. Most astronauts are from the military, but you can also do it the scientist route. If you do it the scientist route, if you can pick a field where you have to go out into the field and actually, like, for example, there's astrophysicists who go to Antarctica or volcanoes, or they go to the most extreme environments in the world and they look for life in those extreme environments, because if it can exist on Earth in those extreme environments, perhaps it can exist on the moon of Jupiter or something like that. And so if you can get field experience, that helps. I think one of the scientists who did get the job when in the most recent round of hires from astronaut for the astronaut class, I believe she studies the moon. I think she's does lunar geology. So I would say for undergrad, physics is a great degree. Geology, if you want to do astrophysics, find a good strong physics program or astrophysics program. If you want to go to the planetary science route where you're studying things like Mars instead, or even the moon, you can have a geology major. I personally think the physics major is very useful. So yeah, that would be my advice. And if you can get flying, having your private pilot's license will help with your application to be an astronaut as well. And they also like to see that you can blend in to other cultures. So if you can learn a language. They also like athletes. So yeah, you just have to be the best at everything, basically. So but I would start with, a physics degree.
Great.
Or any other science. Yeah.
Go ahead.
Hi, thank you so much for the presentation. Just a real quick question, your perspectives on the administration's moves to defund NASA and to privatize NASA and its implications for science?
Yeah, so I am not allowed to speak on behalf of NASA. However, I am allowed to speak as an individual. So everything I'm saying from now on is my, feelings as an individual that works at NASA. So it was pretty dire, to be honest. So for background information, the administration proposed to cut NASA's science funding by 50%, which would be what they were calling an extinction level event. Because even losing that much funding for a year, you're losing people who have so much knowledge that you're losing so much knowledge by doing that. And so actually I now live in Washington, D.C., and there's this group called the Planetary Society, which was started by Carl Sagan, but now it's run by Bill Nye, the Science Guy. And actually, over 300 of us, including Bill Nye, I should have showed you guys the picture of me with Bill Nye. I got a selfie with him. But all 300 of us went to the Capitol, and we went and spoke to our representatives. I was in the Oregon, since I was in DC and I can't vote there anyways. I went with the Oregon group, so Oregon and Alaska were put together, and so I got to talk to our representation from Oregon. And like I said, there was 300 of us, and after that event, Congress was actually very supportive of funding NASA, and they actually pulled through, and NASA is now funded as much as it was funded last year, which is amazing news. But yeah, there's damage has been done still, because while we thought the budget was going to be cut in half, people were allowed to take voluntary leave, and a lot of the more senior folks took voluntary leave because they didn't want junior folks to have to leave instead. And so, and the senior folks have a lot of knowledge that they still need to pass down, and so it's a huge loss. But we do have funding now, fully funded from Congress, but this is going to be a struggle every year until we'll see. But I'm happy that we are now fully funded. But according to coworkers, it's been the hardest year at NASA's seen in decades. So
no doubt. There's a NASA facility here at Vandenberg, as you know, and some AAUW members are senior management there. And it's been a really challenging environment because of the loss of knowledge and the implications on science. I think that's key too.
Exactly. Yeah, because exploration was still funded, was going to be funded no matter what. They still want to go to the moon and Mars, but they were going to cut science, not realizing that, science is the future, and that's how humanity progresses and all of that. So yeah, I'm glad that we do have full funding now, though.
The fight continues. Thank you very much.
Mm-hmm.
Why did you choose to make the film? From Karen.
Yeah, that was a really difficult choice to make. I didn't know Sandy at the time. Sandy's the director of the film. But we had a mutual friend. How Sandy found out about me was through our mutual friend. She was actually one of my teachers in Canyonville, my cheerleading coach. And so that's who told Sandy about me. And eventually Sandy asked for my email and phone number and told me that she wanted to make a film about me. And we talked a few times, but eventually she flew to Tucson with a life story rights agreement. And that was scary. It's also scary to just put your life in a movie, so it took me a while to say yes and to sign that life story rights agreement. But during that meeting with Sandy in Tucson, I asked her why she wanted to make the film. And she said that she felt that if people could see me survive what I've been through, it could help them get through hardships of their own. And as you know, the worst day was very public. It made national TV. And over the years, I have gotten messages from random strangers that said, that exact same thing. And so I felt like our goals were aligned. And my friend trusted her, and it turned out to be a great decision, because now Sandy's one of my best friends. And so I don't regret it, but it was a hard decision to make, definitely.
And let's see, Karen again, how is JWST able to take these beautiful pictures? Is the galaxies and universe really that colorful?
Yeah, so with JWST, so it does see infrared light, but the way that the universe is this colorful, the way that we take these images is we take a picture with a filter on it, and it only lets in, say, red light, and then green light, and then blue light, and we stack them together. Of course, we can't see infrared light, though, right? So the infrared light would be invisible to us, but they do stack it in a way to where the longer wavelengths are redder and the shorter wavelengths are bluer, just like how our eyes see. But yeah, 30 years ago, the technology to take images like this did not exist. In fact, the person who's largely responsible is my PhD advisor, Marcia Rieke. She's worked on JWST for 30 years, and she spent her career making the best infrared detectors that you can make, including, NIRCam, which is the main camera on JWST. In fact, she's known as the mother of infrared astronomy for that, and for all of the other, breakthroughs that she's made in the field. And then her husband, he made the other camera. So they're just a power. Yeah, he's the father of infrared astronomy. He built the camera that sees the even redder wavelengths of light.
Wow. And Roseanne wants to know, what science path did you take in high school and how did it help? And she admires you very much, by the way.
Oh, thank you. So unfortunately, my high school did not have science. I like my biology teacher didn't believe in dinosaurs. That's the type of science classes I took. I did have a very good math teacher. And he, even though I was the only student in the class, by the time I got to my junior year, he was still willing to teach me. He loved math, and he wasn't going to be able to teach those classes, and I think it was fun for both of us, but I was very lucky that he was willing to teach a class where I was the only student. I think you might remember that part in the film where Alicia calls me a nerd for being the only student in math class. So I will say I had a strong foundation in math, but basically no foundation whatsoever in science. In nursing school, you do have to take science. I took anatomy and physiology, intro chemistry. And so I did love that part of nursing school. But of course, physics, I will say it was rough to take physics for the first time in a calculus-based college course. So if at all possible, if you're interested in taking a similar route to me, I would say do as much math and physics as you can, as early as you can. And the other thing that I had to learn as an undergrad was coding. I know the language Python. I would say math and physics are more important, but if you can also get some Python experience, that would help as well.
Great.
Cal Nichols wants to know if you've ever seen anything that looked like life when you're exploring the universe.
There's actually people at NASA currently looking for life. So there's two ways to look for life, and one is called what's called a biosignature. So that would be so the James Webb Space Telescope can look at the chemical components of the atmospheres of planets that orbit stars other than our own sun. So one of the main goals of JWST is to look for biosignatures, which would be, chemicals in the atmosphere that could only be due to life. They are currently searching for that. It has not been found yet. If you see a claim that it has, no, we have not detected life yet. There are also people that are looking for what's called technosignatures. And that would be, for example, if you've seen the movie Contact from the 90s, SETI, that's based off of a real person. And yeah, so there's people looking for technosignatures. So for evidence that there's technology on other planets. That's an ongoing thing with NASA. And our next one of our next big space telescopes is called the Habitable Worlds Observatory. And with that one, I think we're going to find life. In fact, I host this science event in DC, and my speaker that I had this week ago, this is what he does for a living, and he said to the audience, we're going to find life in our lifetime. We will find life. It could also exist even in our own solar system. For example, the moons of Saturn or Jupiter, they have icy shells, but underneath that they have liquid water oceans that are warmed by volcanic activity, similar to how we have here on Earth. So it's possible there's microbial life in our own solar system. But according to an expert, he thinks we're going to find it in our lifetime.
Wow. Mary Pat, could you go ahead and ask your question?
Thank you very much. First of all, it's just fantastic. If I understood you correctly earlier when you were showing your video, you said that the dust that comes for the later stars comes from exploding stars from before, yes? And
Yep.
that leads to more developed or complex stars, I presume. But then you also said, if I understood correctly, I'm not a scientist, that you were surprised, or you and your other scientists, that earlier stars were more developed than had been anticipated. So how is that? If they develop because of prior exploding stars, yeah, how are the early ones developing?
Yeah, exactly. That's something that I'm going to keep looking into. I'm about to publish this paper. It's I just have to finish my referee report, but yeah, that's the question that we need to answer. I think it could come down to the fact that the first generation of stars, since they were born in very different conditions, it was much hotter back then, much denser, and also they formed out of pure hydrogen, basically. We think those first stars we know that they must have looked very different than how stars form in the nearby universe, in those pretty pictures like the Eagle Nebula and the Pillars of Creation. And so it must have to do with what those first generation stars look like, and how quickly they live, and also the elements they produce in their deaths. I think it's going to come down to trying to observe first stars.
Thank you.
Okay, Cassidy, go ahead.
I was wondering, how can I get into your program? With all you said, that the Woody Stars program with getting stuff like that.
Yeah, so currently for Woody Stars, currently we only accept students that are at the University of Oregon, but we're trying to expand. So currently all of our stars are taking physics classes at the University of Oregon, but we do want to expand. We're looking at expanding to Arizona, perhaps. But yeah, that's something that we're looking into. But for now, it's just Oregon, just because that's where Dr. Fisher is, and so it's easy to do in just Oregon for now. But feel free to email me, Cassidy. Yeah, feel free to email me, and we could even Zoom together if you'd like. I like your shirt too, by the way.
I don't know if we've had this one from Cynthia. If the universe is expanding and galaxies keep evolving, does that mean stars will continue to form forever?
I mean, forever, no. Unfortunately, the most likely, the most likely end of the universe is going to be what's called heat death. Everything's moving away from each other, and eventually, all the galaxies will be so far separated, and you'll have what's called a heat death. And so, yeah, if that's how the universe ends, that's the current theory. But this is still very much an open question. If the universe keeps expanding, though, no, stars won't be able to form anymore. Everything will be too far apart from each other. But that'll take, I don't even know how many billions of years, if not trillion. Yeah, that'll be a long, long time away.
Sandy asked, what's the difference between galaxy people and planet people?
Oh, she's making fun of me. So in astronomy, people, like, we call people based on what they study. So like, I'm a galaxy person, and we tend to look down upon planet people, who are the people who study planets, but they also look down on us. There's also star people. The theorists look down on everybody because they're the smartest and they're just doing math all day. So they have the right to look down on everyone. Actually, when I was at this event to stand up for science in DC, I met a neuroscientist, and I told her that. And she was like, oh, we do the same thing, but she studies on, she's like, so there's the gnat people, and then there's the frog people, and she's like, and then there's the people. So they have it even weirder over in neuroscience. But yeah, Sandy's making fun of me because I call people planet people and star people.
Somebody wanted to know, how hard is it to get a PhD?
It's pretty difficult. For me, it helped that I really love the material. So it is going to be difficult. So only do it if the career you want afterwards requires the PhD, and also if you love the material, because you're going to need, for me, I needed to fall back on my passion for it at times, because research is really hard, and it doesn't go the way you want it to go. The universe doesn't listen to you. And so, yeah, and it's, good to have hobbies and stuff like that outside of it. That's why I said, flying airplanes was fun, because I could see progress pretty immediately, as compared to sometimes in research, progress feels like you're not making any at all, even though you are. But it's hard, but it's doable.
Larice said, I believe that I heard you, one image is the size of a fingernail tip. Did I hear that right? You're studying fractions of the universe, one fingernail size at a time.
Yes, quite literally. Yeah. Actually, though, so the next space telescope, it's actually pretty much finished being built, and it was named after a woman, the Nancy Grace Roman Space Telescope. So if Hubble can see only this much of the sky, the Nancy Grace Roman Space Telescope can see this much of the sky all at the same time and with better clarity than Hubble. So we have that launching very soon. And JWST only sees like a tiny, tiny part of the sky. But yeah, we do it fingernail by fingernail, kind of like a quilt, almost like patchwork on a quilt. So once the Nancy Grace Roman Space Telescope launches, which I think is supposed to happen in a year, then we will it'll be way more, we'll be able to have a bigger quilt, much, much bigger quilt.
All right. And Sandy asked a question, I don't even know if I understand it. Regarding the Hubble tension, I saw a paper suggesting the non-homogeneity of the universe today regarding gravitational variation, suggested that may account for it. What do you think?
Honestly, I would have to look into that. I'm not sure about that. Yeah, I would have to look into that. I don't think I've seen a paper about that. I can look into it later, though.
If you didn't major in what you do, what do you think you would be majoring in today, or what career path would you choose?
I mean, I might do what I said earlier and try to find something where I could do field work and go to like Antarctica and stuff. So like astrobiology would be cool, where you're looking, I mean, I think they mostly study tardigrades, which are these little creatures that can live in the vacuum of space, and they can live in all these crazy environments. But or particle physics is pretty cool, so, like CERN, smashing atoms together and seeing what comes out. That would be cool too. But yeah, physics is still high on the list, and then maybe particle physics, and then astrobiology, something like that.
Great. All right. Well, I don't know if you realize that we have 8th graders here, we have college students here, we have all sorts of people who are here asking questions. I think it's pretty amazing.
Yeah, that's awesome.
One person who used to teach said she used to tell her students when she taught PhD students to leave the program unless they had a fire in their belly, because you need a fire in your belly to get through.
Yep. If I quit my job at NASA and went and applied to what we would call industry, which is anything that's not in academia, I guess, I would start out making at least double what I make right now. And so, yeah, you don't get paid very well. And you're expected to work long hours sometimes. And so you have to really love it, because, yeah, I could quit my job and go buy an airplane instead or something with the money I would make. But I love my research too much that I'm willing to get paid less to keep doing it.
Asha wants to know, what's the best telescope in the world?
Oh, of course, it's the James Webb Space Telescope. I'm part of the team, so of course I'm going to say that.
Any others, Nancy, that you saw?
I think we've covered most of them, and a lot of thank yous are coming in now.
Thank you guys so much. It's awesome how many folks showed up.
Yeah, and all of us, anybody from either online branch, would love to invite you to join our branches. It's your choice.
Yeah, I would love that.
Online. Yeah. And it's a great way. It doesn't matter where you live, you can be a member. So.
Right. Yeah, that would be amazing.
How is it possible for the universe or galaxies to evolve?
How is it possible? Time. entropy. Time, really. Yeah. It's just at first we just only had hydrogen, and honestly, the answer is because in the very early universe, everything was almost exactly the same everywhere, but there was tiny, tiny fluctuations in the temperature. And this allowed areas to clump together more than others. And so that was the seeds for what in the future would become galaxies. So basically, it comes down to because the universe wasn't perfectly symmetrical all the way across. And because of those tiny little fluctuations, very soon after the Big Bang, that led to having galaxies and, stars inside those galaxies and everything. But yeah, the universe is, what is it? It's like around 25% dark matter, or around 20% dark matter, 75% dark energy, and then the rest is the regular material like hydrogen. Everything that we know about is only 5% of the universe, and so there's still a lot of questions we have to answer that.
Somebody wants to know, why is Jupiter your favorite planet?
Why is Jupiter? When I, as an undergrad, when I was taking undergrad astronomy with Dr. Fisher, I was reading about Jupiter in the textbook, and it just freaked me out a lot. So Jupiter spins around, I think a day on Jupiter is only 9 hours, and it's huge, and it has a metallic core. And anytime you're spinning metal, that's going to cause a magnetic field. The magnetic field is crazy huge on it. And so it has aurora that are thousands of times brighter than the aurora on Earth. It's just, and then the storm is bigger than the Earth. Like there's that great red spot that's existed, for I forget how many years now, and it's bigger than the Earth. I don't know. It just freaks me out reading about it. One of the things I used to always wonder is what freaks out astrophysicists, and so that's something that I always ask. And yeah, so for me, Jupiter is one of those things. And then a lot of people say just how many galaxies there are. Some people just say time, and that's it. They end it with just one word answer. So yeah, I don't know, just things like that keep you up at night. They're just intriguing to me, I guess, including Jupiter.
The documentary is still available until the end of the month, until January 31st. So you can still use the key to see the documentary. And if you haven't seen it, please see it. It's wonderful. I'm sure you have tissues.
Not yet.
Also in the chat, someone put spacehopecharityfilm.com.
Yeah, you can order DVDs from the website. And it's not on YouTube. It's we are looking for it to be on public TV, like PBS, for example. I know actually Sandy had a meeting with Oregon Public Broadcasting. Hopefully it'll be on public TV sometime in the future.
I ordered the DVD, and it came in just a matter of a couple of days, and it's wonderful, and I've watched it again. So
thank you for
probably
doing that.
We'll do it again. Yeah.
Thank you.
And you got that from Space Hope Charity.
Exactly. Well,
film.com.
Yes.
Yep.
Actually.
I'm sorry, if I
Sandy?
could jump in for just a second. We don't have it available to the general public for free because we're streaming it at a cost. But for AAUW, for this limited period of time, you have a license to watch it. But we would just ask that you please not share that outside of AAUW. Feel free to share the spacehopecharityfilm.com website with other people outside of AAUW. They can either stream it for, I think it's $12.99, or they can buy a DVD for around $15, including shipping. So, thank you. We appreciate your respecting that.
Julie Skinner, is Julie?
There I am.
Oh, Dr. Carloni. Oh, sorry.
So yeah.
Hi.
Hi.
Oh, sorry. my professor from the Umpqua Community College in Oregon, Dr. Carloni. He's actually one of the reasons I became a scientist too. He was a lot happier than the nursing professors were, and he had a passion for his science that was really infectious. And so I saw his name on there. It's so good to see you, Dr. Carloni. Sorry, I didn't mean to interrupt you, Julie.
Okay, I don't have much to say, but I'm glad you included us from Montana in this, and I hope we had quite a few participants. Glad I was able to provide the link, and it was a great program.
Thank you.
I want to thank everybody for coming. It's so marvelous that so many people were able to come. And thank you again, Dr. Charity Woodrum, for sharing your expertise. I know you're exhausted from all the flights and the connections, but your passion for your subject comes through, and your passion for helping the younger generation, your passion for teaching. No matter what you're doing, you're still teaching everyone. Thank you. Thank you so much. And please stay in touch with us all.
Thank you. Thank you for hosting this event and for everyone that showed up. So many people showed up, so I'm very grateful.
Thank you. Get some sleep. Get some rest.
Okay. Thank you all.
Thank you again for coming.